Okay, so hi everyone. In this lecture, we'll discuss numericals. I have four questions to support our discussion, what we have discussed in the last lecture. Okay, so these lecture, those who have not understood properly or those who are having a few doubts here and there in the last lecture, please listen this lecture carefully. Please see how to you how am I using those equations. If I will say, if I talk about the different kind of ratios I have talked about, right? Structural ratio, then payload ratios, then how to use those equation in calculating the velocity gained by the rocket, right? Then later I talked about the burning rate, burning rate law. So that question to support those theory, again I have taken a question. So that similar kind of question has been asked in the GATE exam. So now I think you will appreciate those two questions when we'll solve. It will be very much clear. I'm 100% sure. If you are having a doubt, I'm assuming that some student will be having a doubt on the burning rate law because I have not given in terms of the numericals. So probably some of the students will be having a doubt. So it will be very much clear at the end of this lecture. Okay. So let me start with the uh, this question. I think this question was I have given to you in the last lecture, right? To solve you, but let's see the solution. Okay. Let me read this before that. Yeah. Okay, so let's read this. An ant burning grain, propellant grain of a length of 0.6 meter takes 100 seconds to burn over its entire length at a pressure of 3 megapascal. So don't move forward till to stop yourself at till this point. Now let's understand what data they have given. So there is a propellant ant burning propellant grain. That means ant burning means there is a cigarette burning grain. Once you start burning, it will burn in a one shot, right? So there is a one kind of this kind of shape of the grain you are having. It is circular. Okay, it is generally not generally, it is always circular, and burning grain is circular. So you start burning from here, right? That means you start burning from here, will burn along this way. So the length of the grain is, this is the grain. Okay, so this is the grain. What is the length? Length is, they have given 0.6 meter. Okay, always also see the units carefully. Okay, the unit which they are talking about, the unit what we have seen, that for the specific case, if they have provided this kind of unit, then you need to, okay, I'll see, well, that I'll let you know how to capture this unit as well. And time taken to burn from here to here is given by 100 second. So that means at 100 second it will be completely burned. Okay, and the pressure, that means I'll write this as a, let's say, PC, or we can also write this as a P naught, combustion chamber pressure. Okay, is given as 3 megapascal. Okay, this is what they are given. Now let's read further. The burn rate increased to 120 second. Now burn rate increased, so let's say again same grain. Okay, now the length is also same, it is constant. Now burn rate increased to 120 second, not by. Okay, by is different. It is increased to 120 second. When it burns at a pressure of 2 megapascal. So when you keep your pressure 2 megapascal, then it takes this time duration. Okay. Okay, assuming the linear burn rate law, which is given by this, I know, and we already know this equation, right? In the last lecture we have discussed. So the linear, sorry, so this equation is given by a PC to the power n. This is the constant value for a specific for the, so the what temperature you fill your propellant or store your propellant inside the combustion chamber, that depending on that you have these a values. Okay, and PC, they have given two different values, and this is combustion chamber pressure. I can write PC or I can write P naught, one and the same thing. Okay, so let's write C as of now is valid. So this is we had already seen this, right? So they are saying is it is valid with R given in meter per second. Now R given in meter per second when pressure is in Pascal. Okay, so this is very restricted and stringent, that you need to substitute pressure here in Pascal, and then if you substitute, you will get R value in meter per second. That's what they are saying. Okay, find the exponent, and they're asking us to find the exponent and value. Now how to compute this? Now pause this lecture, think about it, and try to solve the question. Okay, so let me give it a try. Okay, so what I'll do, it is very simple now. I know I told you that they'll give in a two different ways, right? So they have given in the second way, that is R. What is R? This is meter per second, the speed at which your grain burns. Okay, so the length I told you, right? They will give in terms of the length. So they have given in this question. So length they have given. So it is simple distance by time. So everything is given now. Distance is also given, which is 0.6 meter, and time is given this as 100 second. And if you solve this, it will comes out to be 6 into 10 to the power 3 meter per second, right? So let me give this as a R1. Okay. So this case is case 1. This is case 2. Okay. Now what we'll do? We'll do R2 calculation. You'll come to know why I'm doing R1 and R2 calculation. Okay. Because let me give it a try here itself. Because I know what I can do, I can use this R1 and R2 and a PC value power n. Similarly, a PC value power n. This a and a will get cancelled out. Okay, so this will be gone. You're left with the pressure value of a combustion chamber pressure value. And at the end, I know these two quantities. I can simply calculate n value from here. So this is that is the reason I'm doing calculations for R1 and R2. Yeah, I hope it is very much clear to you. So again, let's calculate R2 value from here. R2 will be similarly again distance by time. So for this case, distance will be still it is same 0.6, and time is this time it is taken 120 seconds. Solve this, you'll end up getting this as a 5 into 10 to the power 3 meter per second. So I got R1 and R2. It's very straightforward now. Substitute all the values. R1 is 6 to the power 6 into 10 to the power 3 minus 3. This will be 5 into 10 to the power minus 3. A and A here it will cancel out because this is constant for both the propellant grain, right? So it is constant. So now these both the things will be cancelled out, and now this is PC1 and PC2. Okay, so combustion chamber pressure. What is combustion chamber pressure for case 1? It is 3 megapascal. So what you need to do, you need to substitute in Pascal here. But I'll tell you, it doesn't make any sense here now, because so specifically they have stressed on that P should be in Pascal to have R value in meter per second, right? Meter per second. But when you substitute in Pascal here, so numerator and denominator 10 to the power 6 will cancel out. Okay. So this doesn't make any sense. You can substitute in Pascal, you can substitute in megapascal, one and the same thing. So let's substitute in Pascal so that it will be very much clear to you all. So this is 3 megapascal they have given. So let's substitute, convert it into Pascal. So you have to multiply 10 to the power 6, and here it is 2 megapascal, 10 to the power 6, and so I'll write in this way. Okay. So solve this, and what you need to do, you need to take ln. Okay. So on the both the side, you take ln, and you'll end up getting this as this value will comes out to be 1.2, and will come out. And if you solve this for ln, this value I'm getting this as a 0.405. Solve this, and you will get this as a 0.445, and this will be approximately 0.449. This will be 0.45. So now you got n value. Okay, so this was a numerical. Option B is correct. Okay, so I hope now it is clear that even you see the range which I have provided for n value, which was 0.2 to 0.8 in between, right? And this is positive n value. Positive n value means you cannot stop the grain, right? It is not a restartable grain. That is the reason, and it is also the end burning grain. That means positive n value and burning grain, one and the same thing. It will be burning by one shot. Okay, you cannot stop the burning in between. Okay, so I hope this is clear. Now I'll give you one more question to make my points. Now I was interested to solve this question. Okay, please pause this lecture and try out by yourself as well. Okay, fine. All right, so okay, so please focus on this question. I want your high attention on this. Okay, question has been on, and question are asking from this concept. Okay, okay, yeah. Okay, so let's solve this. Okay, first let me read this. Find the study. Okay, find the study chamber pressure of a liquid propellant rocket. Okay, when the propellant burning surface area is, this is what they are given. So they are asking us to calculate the chamber pressure, PC, or you can write P naught. P naught, right? They're asking us to calculate this combustion chamber pressure of a solid rocket, propellant rocket, when the propellant burning surface area is 2 meters square. So what is the surface area? So they have given SB, but in our notation it was AB, burning area, right? So this is given by 2 meters square. Okay, use the following data. Okay, the characteristic velocity of the rocket is C star, which is 1750. So C star, I know this is, we have already studied about this. This is C star, this is given as 1750 meter per second. Propellant density, now you can see how high density it is. So propellant density, I'll write this as rho P and 2500 kg per meter cube. All right, everything is, we are on the same page. We know everything, each and every term is known to us, right? Now they have given the throat area A star, which is 0.01 meter square. So what is the throat area? Nozzle throat area. Okay, right. The linear burn rate law is given as, okay, so we have again studied about the linear burning rate law, and this is given as R equals to 0.015 p to the power 0.4. So this is what they have given to us, right, where R is specified in mm per second. Now you see they have given in mm per second, provided that your pressure should be in a Pascal. So what I'm saying is R value now it is in a mm per second, and your pressure should be, that means I'll write this as a P naught now, or I can also write this as a PC, one and the same thing. Okay, so P naught they have given this should be in a Pascal. So you cannot substitute here pressure as a megapascal or some other value. You cannot do this. If you do, because this equation is already defined in terms of the Pascal, and R value you will get this in a mm per second. So you cannot change this. Okay, if they will say this as a meter per second and Pascal should be in a pressure should be in a megapascal, then you will substitute pressure as a megapascal. So in this question they have provided this as a mm per second and Pascal. In the previous first question which we have discussed, and yes, this question was, yes, you see R value was in meter per second and P was in a Pascal. So they have defined in their way. You cannot change this. If you do, then you will end up getting this as 0 marks. Okay, so you should restrict yourself to put the values in which what they have defined. Okay, so okay, I hope you understood. Now they are asking us to calculate the pressure value. What should be the combustion chamber pressure? So now how you will proceed for this? That is the question, right? Okay, if you are thinking that we can start with the C star, that P naught by A star divided by M dot P. So the thing is, you know C star, you know P, you don't know the P naught, you don't know the M dot P as well. You know A star, but you the two quantities are unknown in this equation, so we cannot start with this. But the thing is, we need to compute the M dot P here, and if I'm able to compute the M dot P in terms of P naught, my numerical will be over and I'll getting the 2 marks in my exam, right? So what I'll do, I'll take this formula, I'll use this formula, okay, and I'll compute M dot P from here in terms of P naught. How we'll do this? I know that, right? P naught M dot P is nothing but what? Area, density, area, and velocity. So density will be what? Density of propellant. What is the area? This should be the burning area. Okay, and what is the velocity? Velocity will be R, propellant burning rate, propellant burning velocity, or propellant burning speed. So R now must be in a meter per second. Why it should be in meter per second? Because my M dot P itself is defined for kg per second. And if you want M dot P in kg per second, everything must be in SI unit. What is the SI unit? Kg per meter cube, meter per square. R is velocity should be in meter per second. Okay. So if you see here your R value is mm per second. So you need to be careful, be cautious. You need to convert this at the end in meter per second. So what I'll do now, I hope you are getting my point. What I'll do, I'll take this equation, because everything is here known to us. Okay, just give me a minute. Yes, R I can take from here and substitute it here in terms of meter per second. Okay, how we can do this? R can be written as 0.015, P naught 0.4, and you divide this by 1000. That means 10 to the power 3. I can do this, right? And this complete will become, so now R will become in meter per second. Now I can substitute directly in this equation, right? I hope you are getting my point, guys. So m dot p will be, now density is how much? 2500 kg. What is the burning area? Burning area is 2 meter square. So I'll write this as a 2, and I'll write the r value here. So 0.015 p naught to the power 0.4 divided by 10 to the power 3. Now you simplify this equation, you'll end up getting this as a, okay, if you simplify this, so if you solve this much, okay, you'll get this as a, I am getting this as a 0.075 p naught to the power 0.4. Okay, so this is what I'm getting. Please verify this whether you're getting this coefficient or not. Okay, now what we will do, I'll substitute m dot p here, because if I substitute m dot p, this m dot p here, I have already p naught here, right, and also p naught here. At the end it will cancel out. At the end I'll be easily able to, because here it is in a power, okay, 0.4, and what is the power here? 1. At the end I'll get p naught from in this equation. Only the only unknown in this equation is now p naught, which is combustion chamber pressure. So now what we will do, I'll substitute m dot p in this equation. So c star is 1750 meter per second, right, and m dot p, if you substitute, okay, this will be 0.075 p naught 0.4. Now p naught will still, this is unknown quantity. A star is 0.01 meter square. You ensure that everything must be an SI unit in this equation. Okay, that is why area is already in meter per second. Here area was already in meter per second, right? 2 meter square burning area or surface area. So you solve this, what you need to do, 1750, you keep it 0.075 divided by 0.01, and here p naught divided by p naught to the power 0.4. You simplify this equation, you'll end up getting this as a 13125. And what you can do now, this you send this because base is similar, right, p naught and p naught, so you can do 1 minus 0.4, and then you will get this as a 0.6. Now you take ln on the both the side, ln on both the side, here and here, you'll end up getting this as a, okay, let me do this. So you take ln to this quantity, you will get this as a 9.4822, and 0.6 will come down, and ln will be ln of p naught. You solve this, and p naught you will get this as a, so now tell me what p naught value you will be getting. P naught value will be in meter, in a pascal or in a megapascal. Tell me this. This should be in pascal, guys. It cannot be in megapascal. Okay, everything was in SI unit, so this should be also in SI unit. What is the meaning of it? Because you can also calculate that it was in meter per second. Okay, then this area was in meter square. You do the unit balance, you will get this as a Newton per meter square you will get. Okay, you can do this, you can try out this. This is a good practice for you. So you will get this as a 730,295 8.85, and this will be in pascal or Newton per meter square. But the question was, they were asking, they have given the option in megapascal. So what we need to do, we need to divide this whole equation by 10 to the power 6, and p naught, or you call this as a PC, you will get this as a, okay, you will get this as a 7.3 megapascal. So this is your answer, and option B is correct in that case. So I'm assuming that everyone is crystal clear with each and every step, how we have proceed for m dot p calculation, how we have used this equation then, and how I have converted this equation from meter per second to mm per second to meter per second. Okay, be very cautious, very cautious, that when they have defined this equation in terms of these two quantities, everything should be in the provided quantity. Okay, I mean to say that if they have said here should be pascal, then put pressure as a pascal, and whatever r value you're getting, that should be in mm per second. But if you required in meter per second, you can convert this, provided don't touch the value of p naught. Okay, so this was okay, fine. I hope you're understanding each and everything, guys. Okay, and I hope the two different way of giving the same numerical, I hope it is very much clear to you that how the burning rate law. So this kind of question is already asked in a GATE exam for 2 marks. Okay, so depending on this, once you have done the calculation of p naught from here, sorry, P naught, once you got the P naught value, you substitute here P naught. Okay, they can also ask for the mass flow rate of the propellant. Once the mass flow rate is calculated from here, you can simply calculate the thrust from here. So this is also possible. Then yeah, these kind of parameters you can easily calculate. Okay, so I hope this is clear to you. I'm assuming now burning rate law, if any kind of question comes in your exam or comes in a way, that means if you're solving any test series, okay, burning rate law question, you should not feel difficult. It will be solved very easily. Okay, now let me move to the another question. Okay, now I want to solve this question. So this question is based on the multi-staging of rocket. So if you recall, in the when we were discussing about the multi-staging, I told you that multi-staging is beneficial, okay, in terms of the velocity increment. That point I want to prove with this, with the help of this numerical. We want to understand with the help of numerical and with the help of some numbers. So we will have a we'll have a feel of that. Okay, this much percentage increment we will get from the as compared to single stage rocket when we use a multi-staging. Okay, so that thing we need to understand. Okay, so that those numerical will those concept will make sense. Okay, it is always better to have a numericals, right? Okay, so let's read. So this is your gate, I think, yeah, gate question. Okay, it is gate question. Okay, so it is gate question. They have asked for a 2 mark. Okay, they have asked for a 2 marks in the exam. Okay, so let's try out this. You can also pause this lecture and try out this question. Consider two consider okay consider two rocket P and Q fired vertically up with identical specific impulse. Okay, that means there is two rocket. So let's write, there is a P rocket and there is a Q rocket they have given. Okay, and they have fired vertically up. Okay, and with the identical specific impulse. So they are having identical specific impulse. That means ISP and ISP. I hope you are agree with this, right? Now they are saying, and the payload of a 2 kg, that means payload is also identical. So I'll write this as a ml of 2 kg, and for this rocket it is also ml for 2 kg. Okay, now they are saying rocket P has two identical stage. What is the meaning of this? They are having a rocket P is having a 2 stage and they are identical stage. Identical means the quantity which you are having for a first stage, that means structural mass and the payload mass, sorry, structural mass and the propellant mass is similar for a second stage as well. So this is what the identical 2 stage meaning is. Okay, so the stage they have given this here is a n equals to 2, here n equals to, we are having a single stage. Now they have given two identical states. So what I'll do, I'll draw this diagram. It will make more sense now. Let me draw more better. Okay. Okay. Okay, so it is having a 2 stage. So this I'll give this as a first stage, and this will give this as a second stage. Okay. Okay, so they're saying identical. So here we have a ml of 2 kg. Okay, number of stages 2 we know. Now let's read this further, what data they have given, and the each stage now they're saying each stage has a 200 kg of propellant and 20 kg of structural weight. So let me write this. Now you'll come to know MP and MP here, MS and MS here. So they have given this as a identical, means here it is also 20 kg of propellant, here it is also 200 kg of propellant. Now structural is 20 kg of weight, that means mass. Okay, they have given in a kg, so we'll call it the mass. Rocket Q has a single stage with a 400 kg of propellant and 40 kg of structural weight. So now it is saying that they are having propellant of 4 kg, the structure of 40. Oh, sorry, 40, it is 40, right? 40 kg. Now they're saying neglecting drag and gravity effect, and this is what we know. This is our assumption, right? We never consider the we consider in equation, but now they are saying the neglect the gravity effect. The ratio of change in velocity of P to that attained by Q. Now they are saying you please calculate UP by rocket UP value attained by rocket P to the UP value attained by rocket Q. You calculate the ratio, and this is what the 4 option is given. Now we should understand first that what is the importance of this equation is question is what they are trying to make us understand is that they are trying to say that they are trying to make us understand about the when we consider the multi-staging. Okay, we have a more velocity gained. You can see all the option is having more than one. We have so we when you consider the multi-stage, you have a more velocity gain by as compared to the single stage. Okay, and we'll come to know that it is uh, it is more than the up value. This value is more than upq. We'll come to know this. Okay, and this is your gate. This is your gate question. Fine. So this is the data they have given. Now we need to calculate these two quantity and we'll take the ratio. So how you will proceed for this? So first thing what I'll do, I'll quickly calculate the UPQ value here. So how do we calculate? This can be written as ISP, okay, ln of M1 divided by M2. I should not consider this value because they already told us that gravity effect has to be neglected. Okay, so I should not consider that. So UPQ, if you calculate GISP, they have not provided, so we will not substitute the value. At the end, when we take the ratio, this two will cancel out from numerator and denominator. So we should not worry about this. So let's keep it same. Now what is the M1 value? So your M1 value is the initial mass of the rocket. What is the M2 value? Is the final mass of the rocket. Now we need to calculate the initial mass. Now what is initial? How you calculate the initial mass for a rocket Q we are talking about? Okay, so the initial mass is MP, MS and ML. So you substitute this as a 400 plus 40 plus 2. And what is the final mass? Propellant is gone. When propellant, so M2 is nothing but M1 minus MP, right? So when propellant is gone, so it is just 42, right? You can do this, you add this and you take subtraction of this 400, you'll end up getting this 42. Now UPQ will be GISP. You take ln of this, you simplify this and you'll end up getting this as a 2.353. So this is the UP value. Okay, UPQ value. Now we'll calculate for rocket P. And now we need to take care about the staging of rocket. So now please understand this properly. This will give you marks in exam. Okay. So we are doing, let me write just UP, and we are doing for a first stage. Here we need to consider first stage. So GISP. So we need not to worry about this because this is constant for every stage, right? GISP ln of M1 now. ln of M1 by M2. G minus of GTP we need not to consider. Gravitational losses we need to neglect. The question itself they have provided this statement. So the thing is now the catch part is M1 and M2 calculation. How you need to calculate this? How you will do this? So please see this carefully. So when you calculate the M1, you need to calculate you need to take the complete mass of the rocket. So what is the complete mass? This is simple. So complete mass of rocket in a sense, first stage, then second stage, then the payload value. So this will be simply 200. So first let's write for the first stage, 200 plus 20 plus similarly 200 plus 20. I'm going by the very basic, otherwise I can directly write 442. I can do this, right? So I'm going very basic way so that everyone can understand. Everyone should be on the same page. Okay, so this is the M1. Now when you write for M2, again propellant mass should be subtracted. Now when you subtract the propellant mass, you should subtract for the first stage, not for the first stage and second stage. Don't do this mistake, okay? Because we are calculating for the first stage. Okay, first stage data we are calculating. So only the first stage propellant will be subtracted. Okay, so how you will write this? This will be simply this much. This is gone. This is gone. Okay, so this will be 20 plus 200 plus 20 plus 2. Now when you solve this, GISP ln of this will be 442 divided by 242. Okay, so now this is your, now please solve this. When you solve this will be GISP and you will end up getting this as a Okay, I have, okay, just a bit. So, okay, ln of it will be, yes, 0.602. Okay, so this is for a first stage. Okay, UP value for a first stage. What we'll do, UP value for a P rocket will be what? UP1 plus UP plus this will be UP1 and UP2. Addition of these two will give you the total velocity for the P rocket. Okay. Now we'll similarly calculate for second stage. Now, so how you will do this? Now please listen this carefully. Now when you write for second stage, okay, this we are doing for a second stage. Don't forget. So this will be, now when you are talking about second stage. Okay, please see this carefully. You're talking about the second stage. So that means when you consider for a second stage, when you write for the second stage, your first stage propellant is already gone. Okay, it is already gone when you were considering about the second first stage. Now this is gone. This is already gone. Okay, this is gone, right? Now when you are considering for the second stage, your this structural weight will be also, this will be went off. Okay, that means what I'm saying is, in simple word, when you do the calculation for the second stage, first stage propellant is already gone, it is already burned out. Now there is no point of holding the structural mass of a second stage because it is not serving the purpose of burning the propellant. Burning propellant is already gone for my first stage. So the second stage mass is it is it is reducing my the rocket velocity. So there is no point of holding this ms value. What we'll do, propellant is gone, right? So we eject the structural mass as well. Okay, so now your propellant mass is also gone. Now the structural mass is also gone for the calculation of the second stage. Okay, so that means when you write for the M2, okay, when you write for M1 and M2, this will be 200 initial mass. M1 will becomes the 200. That means this much we need to consider. Okay, 200 plus 20 propellant and structure for a second stage, and the ml value, what is the payload mass? Payload mass is 2 kg. Similarly, okay, I hope it is very much clear. What I'm saying is, now m2 will be m2. Now this is already gone, we need not to worry about this. This is already gone. Now you focus on this. When you write for m2, your propellant mass will be gone. Okay, you should not consider that. So this will be just 22, 20 plus 2. Okay, so when you solve this, this term will be 222 divided by 22. Now you solve this ln of so what you need to do, up will be simply up1 up2. You take this isp, this isp and this isp common, okay, from both the side, from the both term. This will be gisp and this will be 0.602. And if you solve this one, you will and take ln of this as well, ln, so you'll get this as a 2.3116. okay, I hope it is clear how I'm writing this term. Okay, you just need to add this term and this term. Okay, you take gisp common because it is similar for my p rocket and for q rocket, so we need not to worry about that. So now you just need to simplify this and take ln of, okay, we have already taken ln, so this will become 2 point, sorry, 2.9136. Now we just need to take the ratio up by uq. We can do this, right? Let me do in this way, p rocket and q rocket. So this will be, this is for p rocket, right? So g isp 2.136 gisp and this value 0. Sorry, not this value. This will be this one, right? 2.353. Now you, this 2 will get cancelled out from the both the side. from the numerator denominator, and you simplify this, UP of P rocket and UP of Q rocket, you'll end up getting this as a 1.23. So this is your answer. This option B is correct. That means what now this expression is telling us? So your UP rocket P rocket velocity is 1.23 times higher than Q rocket velocity. This is what it is saying. That means 23% higher velocity you are getting when you are using the same rocket, when you are using the multi-staging rocket. Still you are using the same value of masses. You can see same value of propellant carried, same value of payload carried, and say in this same value everything is same. The advantage which we are getting is when we are writing for a second stage, we are also ejecting the first stage of structural mass. So that is the advantage, then, that when you eject this value and this value, you will have a higher velocity gained. Okay, and that is the reason we always prefer to have a multi-stage rocket. Okay, because it gives the more velocity as compared to the single stage rockets. Okay, now it is very much clear that we have a 20% more increment. Okay, I hope it is very much clear to you guys. Okay. Now we have solved 3 numericals. Now I'm having this last numerical, then we'll wrap up this rocket propulsion. Okay, so let's quickly do this question as well. Then we can, yeah, let's read this. Now again, this is the second question on multi-staging. I'll give it a try. I'll try to explain many more things in this. Okay, a two-stage rocket of a total mass of this much is used for launching a satellite into an orbit. Okay, the detail of the stages are given in a table. So this table they have provided. The stage 1 is ejected as soon as operation of second stage starts. So we know this, right? This is the key feature of the multi-staging rocket. Neglect the gravitational losses, but that's what they're saying. Now they're asking us to calculate the payload mass, then the ideal velocity increment for the first stage. Similarly, the thrust produced, the operational duration of the first stage. Then they're asking the ideal increment of velocity for a second stage, thrust produced by the first stage, and I think second thrust produced by the second stage. So this is what they are asking to us to calculate us. Now this is very straightforward question, to be more precise. So let me quickly draw the rocket so that I can explain you the things. This is what, pardon me for my drawing, guys. Okay. This is your first stage. This is second stage, right? Now let me the given data, they have given, let me write in this rocket. So first stage, this data. Okay, so first stage propellant, mass of propellant is 4,500 kg. Structural mass is 575 kg. Okay, then we have a jet velocity, that means CJ coming out when you use this stage, first stage. This is 2.5 kilometer per second. Okay, this, you see, these are provided in a unit kg. Okay, so this is kilometer per second. The propellant burn rate, that means mass flow rate by the first stage, m dot is 78 kg per second. Please see the unit. Okay, you will come to know what they're talking about. Then the second stage data, they have mp is a 600 kg, ms they have given as a 30 kg. The velocity, jet velocity, they have given this as a 3.2 kilometer per second. Mass flow rate of propellant by second stage is 18 kg per second. You please see this data what they have given. Okay, so this is what they have given. Now we have also ml, but they have not provided. It should be ml, should be present in this. Well, you will come to know. The first question itself is, they are saying that calculate the payload mass. Okay, now if you see, they have given two-stage rocket has a total mass. So what is total mass? Or you write m1. This is total mass. They have already provided 5850 kg. This is what they have provided. Now they are asking us to calculate the payload mass. So payload mass, this can be easily calculated. You subtract initial mass, you subtract the total mass from the, you subtract this much mass from the total mass. If you do this, what is the total mass, guys? What is the total mass? M1 is ml plus you can write MP plus ms for first stage, then MP plus ms of a second stage. So this is your this is your total mass. This is how you write, right? M1 you already know, which is 5850. This data you already know. You take this in this side, okay, for first stage minus of second stage, and here ml. You solve this, simplify this, you will end up getting this as a ml, which is your payload mass, and this will comes out to be, and this value 5075, and this value is 630. Okay, you simplify this, you'll end up getting this as a 145 kg. So this is the payload mass. So they can frame the question in this way to ask for the payload mass, right? So this is, I hope this is clear to you. Okay, so now 140 sorry kg only, right? Okay, now they are saying the ideal velocity increment for the first stage in kilometer per second, corrected up to 2 decimal place. Okay, so how we will calculate this? So this can be calculated by, so we are doing for the first stage, so only you see this data. Okay, so when you calculate for the first stage, you can write this as a G ISP ln of m1 divided by m2. We need not to consider this gravitational losses term, because they already provided us this data, neglect the gravitational losses. So now I can also modify this equation in terms of, so this can be written as Cj, right? So I'll write this as a Cj ln of m1 divided by m2. Okay, I hope this is clear to you. So UP1 can be calculated as, so now everything is known to you. Cj is known to you, they already provided this value. M1 and M2 is already known to you. The only hard work you do is for take care for M1 and M2 calculation. So Cj you already know, which is 2.5, and this is in kilometer per second. So convert this into meter per second. So 10 to the power 3. Some student, they can also do in this way. They already asked in kilometer per second. So there is a, you can also substitute this Cj value in kilometer per second. But let's go with the SI unit so that you can understand each and everything properly. Ln of, I can do this 2.5 multiplication of ln of that m1 divided by m2, that we can do, but still we need to go by your basic. Otherwise, but in the GATE exam, don't do this. Okay, this is not required. For understanding, I'm doing, for your understanding, I'm doing this. Okay, so m1 is what? M1 is this value, initial mass. Okay, so this will comes out to be, or you can also do in this way. You add this term, you add this mass, then you add this mass. You can do this, you'll end up getting this as a this value only, 5858. Okay, divided by, now you when you write for m2, that means we are concerned about the first stage, right? So when you write for m2, your propellant mass should be subtracted, right? I hope it is very much clear to you. So what we can do is, you can subtract 4500 from here. If you do this, you'll end up getting this as a 1350. Okay, now you simplify this, you'll end up getting this as a, yes, 3.6 into 10 to the power 3 meter per second. So what you need to do, they are asking in kilometer per second, so you just need to divide 10 to the power 3. This will cancel out. UP value for first stage will comes out to be 3.6 kilometers per second. So this is the UP value for a, that means ideal velocity increment for a first stage. Okay, I hope it is clear to you. If you are having a doubt from the last lecture, now I'm assuming that it is very much clear to you that how to calculate this UP value for first stage, for a second stage. Okay, now let's calculate the operational duration for a first stage. So how you will calculate the operational duration? That means they are talking about the TP calculation. So this is in a second. Okay, they are asking in a second. So can I write in this way? Tell me, MP divided by M dot P. This is in kg and this is in kg per second. So second will go into numerator. So now this will cancel out and we'll end up getting this as a time. So I can write mass. What is the mass of propellant for a first stage? Okay, they're talking about first stage, right? So I should write this as a TP for first stage. So what is the mass? What is the propellant mass? Is 4500 kg. And what is the mass flow rate of propellant? Simply 78. So this is the reason they have provided this data. Okay, so 78 kg per second. Simplify this, TP1 will comes out to be 57.7 seconds. This is your answer. So I hope it is very much clear to you. Please, you should have this formula ready in your formula sheet as well. Okay, fine. Now let's calculate for the ideal velocity increment for a second stage. Now this is important. You will come to know if this thing is not clear in the previous example. Now it will be very much clear to you. So let's write UP for a second stage. We are doing the calculation. So Roman number 2. So you can again write CJ then GISP ln of M1 divided by M2, but I'm not writing that. I'm directly writing CJ ln of M1 divided by M2, because CJ is given, not G, and ISP is not given, so better to write in terms of this. So now the thing is, this M1 calculation and M2 calculation, CJ is anyhow they have already provided directly. CJ for a second stage is 3.2, this value 3.2. So this will be simply 3.2 10 to the power 3 ln of. Now how you will write for a second stage? So initial mass for a second stage. So when you do calculation for a second stage, first stage propellant is already gone, so there is no point of holding the structural mass. So we should eject this. We should eject this out. We need to eject this, and we need not to consider even. So this is already gone, and this is also we are ejecting. So both this weight is gone. Now we have better increment of velocity for a second stage. So M1 will be what, guys? Now this will be just addition of these two and this one. So if I write this 600 plus 30 plus 145, right? So 600, this is propellant for a second stage, 30 which is structure, and 145 which is payload. And what is the M2? Now you just need to subtract the propellant mass, okay, for M2, and this will be 30 plus 145, this is I think 175, right? So you solve this will be 775. 175. You take ln of this, you multiply this value with the this value and solve this. UP2 you must be getting around this as a, okay, and also divide this by 10 to the power 3. You will get this value in kilometer per second. So this value is 4.76 kilometer per second. So this is how you should calculate for a M1 and M2 values. Okay, I hope this is clear to you. Again, if not, please ask me. Okay, now thrust provided by the first stage. What is the thrust? Okay, one more thing, they have set corrected up to one decimal place, so it is better to write in terms of 4.7. okay, I hope this is also in one decimal place. So yeah, this is fine, one decimal place, fine. Nearest integer, it is already in an integer. Okay, so please be careful what decimal places, still what decimal places they are talking about. Okay, now the thrust produced by the first stage. So thrust can be written as m dot p into Cj, right? Very much straightforward. They are not quite the pressure thrust or pressure values at the exit, the ambient, so we should not worry about that term. Okay, pressure thrust term. I should write one here. Okay, so Cj value already know, m dot p is already know for a first stage, right? We are doing calculation for a first stage. So everything is provided to you. M dot p is 78 kg per second, and Cj value is 2.5 into 10 to the power 3. Now this value will comes out to be, what you do here, they are asking kilonewton, so divide this by 10 to the power 3. This will get cancelled out. You will end up getting this as a 195 kilonewton thrust produced by the first stage. So you go with this configuration, you go with these details, okay, and when you start burning your propellant for a first stage, provided that you are burning with this much of mass flow rate, you'll end up getting this as a this much of velocity, and you will have a rocket velocity of you will be having a rocket velocity of how much? This much, 3.6 km per second, and you will be producing this much of thrust, which is 195 kilonewton thrust. Okay, I hope this point is very much clear to you. Again, now let's do for the second stage. So F2, and this will be again m dot p into Cj for a second stage. So F2 will be, so now what is m dot p? M dot p is I think 18 kg per second, and Cj value is 3.2 kilometer per second, right? Cj value for a second stage, yes, this one. So you will end up getting this as a, you just need to multiply 10 to the power 3. So you will be getting the value in Newton. Okay, You divide this by 10 to the power 3. Now you will get this as a 57.6 kilonewton thrust after ejecting out the first stage mass, propellant and structure. So once you eliminate this, you will have a this much of thrust produced by the second stage and this much of a velocity increment. Velocity after the first stage is gone. So I hope this is clear to you how we do the each and every calculation, each and every parameters when we talk about when we concern about the multi-staging of rocket. So this kind of question they can frame in your exam. Okay, so you should be very much clear that when to consider how to consider M1 and M2 for a first stage and second stage. Okay, this should be very much clear to you. Okay, I hope you understand. You have learned many things from this question as well. Okay. From this question also, burning rate law, I hope now it is very much clear to you. And yeah, again we have done the staging, multi-staging. This question proved us that multi-staging is beneficial. It is giving a 23% increment of velocity even when you consider the same configuration, right? Same configuration in the sense, same weight, same propellant weight, same structural weight, same payload weight. This one. So we have a 23% increment of velocity. And then this n value, right? So I hope now things are getting clear to you. Some of you might be having a doubt from the previous lecture. Now it is very much clear to you. Now probably it is very much crystal clear to you. Okay. Now if not, please ask me. I'll try to help you out in that. Yes. I told you, right, to prepare a short note on prepare a table on specific impulse, right? Different kind of propellant is having different specific impulse. Then also you prepare prepare a short note of types of grain design. Okay, you read about the regressive thrust and progressive thrust, the neutral thrust profile. These are the profiles we were having. So you please study about this. They can frame a question on this. So now I think it is more than enough for rocket propulsion. I'll take another one more lecture on numerical solving. That will be very short lecture. Okay. So now it is your rocket propulsion is over. Now you can start solving your all gate question. And if you are interested to solve more question, if you want to increase your more concept knowledge, you can appear for a test series. You can purchase my test series as well. You can check out. I'll provide the link of my website as well. Okay. So if you're having a doubt again, please ask me. Don't hesitate. Feel free to contact me. Okay. Let's meet in the next lecture, guys. Bye bye.